Hi guys. So we're going to finish up talking about gases by talking about Avogadro's law. We remember Avogadro from Avogadro's number, 6.02 times 10 to the 23rd atoms, molecules, or formula units per mole. And we use that number a whole lot when we were doing conversions and stoichiometry. Well, here we're going to talk about the relationship with gases. So at a constant temperature and pressure, so when temperature and pressure aren't changing, a given volume of gas always contains the same number of particles. So Avogadro figured out that if we keep temperature and pressure constant, 1 mole of gas will occupy 22.4 liters. So that number is a constant that you need to know. So 1 mole equals 22.4 liters for a gas. So just like for a solid, 6.02 times 10 to the 23rd atoms. So let's say we're talking about atoms of helium. That will equal 1 mole. That will also equal a volume of 22.4 liters. And it equals a mass. What is the mass of helium? I think it's about 2.1 grams. So we can see there, Avogadro has added volume. I'm going to highlight this. Volume right here for gases. That only works for gases. So at room temperature, 1 mole of a gas will equal 24.0 liters. So this is at room temperature. Remember STP? What does STP stand for? Standard temperature and pressure. And for that guy, temperature equals 0 degrees Celsius or 273 Kelvin. And pressure equals 1 atmosphere at STP. But at room temperature, which by the way, room temperature is considered 24 to 26 degrees Celsius, in that ballpark right there. So we're saying at 26 degrees Celsius, which would be about 299 Kelvin, 1 mole will equal 24.0 liters. But this is the one that we remember. This is the one we keep in mind. So let's take a look at here. Let's take a look at a problem. What volume of hydrogen gas is produced by reacting 4.87 grams of magnesium with excess hydrochloric acid at STP? So remember STP, our T equals 273 Kelvin, and our P equals 1 atmosphere, just to keep that in mind. All right. So what do we got to do here, guys? We got to balance the equation, right? All right, magnesium, I see 1. Magnesium, I see 1. Here I see 1 hydrogen. Here I see 2. Here I see 1 chlorine. Here I see 2. So I'm going to put a 2 right there to make 2 hydrogens and 2 chlorines. So it balances out on this side. And our magnesiums are still balanced too. Great. All right. So, oh, here it is, answered for you. All right. The answer was there, Miss B. I gotcha. Okay, so we're going back to our conversions from way back when. This is our starting amount of magnesium. We always start with what they've given us. We need to convert that to moles. So right here we have the molar mass of magnesium from the periodic table. So now we have how many moles of magnesium we need. And then we're going to convert this from moles of magnesium that we started with to moles of hydrogen gas that we are producing. And we grab that from our balanced equation. And so we see for every 1 mole of magnesium, we're going to produce 1 mole of hydrogen gas. So that ratio, I'm going to change the color of my pencil here. That ratio we put right here, and that's our stoichiometry. That 1 to 1, that 1 and that 1 come from that balanced equation right there. And then it's asking for the volume of hydrogen gas. So we need to convert that from moles to volume. Well, we now know that Avogadro told us that for every mole of hydrogen gas, that will occupy 22.4 liters. So there's that number, that constant. So that's the constant for gases. And we're going to multiply across the top, divide what we have on the bottom, and we find out that if we start with 4.87 grams of magnesium ribbon, we will end up with 4.49 liters. That's quite a bit. That's a lot of hydrogen, and I'm going to put right here, gas. So that's how we use Avogadro's number there.